record, Zhang? Nice. All right, good night, everyone in Malaysia, I guess. Good morning to Zhang, he's in US. Okay, so we'll be talking about special relativity today, and how we like to do this is, because special relativity is divided into two main parts, I think. So the first part is kinematics, and then the second part is dynamics. I'm thinking of just going through most of the math in the kinematics, and then I'll go to dynamics. If we have time, we can go back to like space-time diagrams, because I'm not sure how much time I'll take. So that's, I think, the outline of today's lecture, I guess. Okay, let's start with kinematics. So, okay, before going into special relativity, right, I would like to talk about just normal Newtonian mechanics, I guess. So let's say, okay, we call this Galileo transformation, but it's just the name of it. Formations. Okay, so usually if I, let's say I have a particle here, and if I want to define its position or displacement, we give it a coordinate x, y, z, and then we say that it's at time t. And let's say we look at it from an inertial frame. So this is x, this is y, this is z. So let's say we have an inertial frame S, and then this particle, when look from this particular inertial frame S, it will have this coordinate x, y, z, and then it is at time t. Now, it looks nice, but then what if we want to consider another frame? Let's say an observer is moving, and then it would be nice sometimes to consider from like what would this observer look, what would the particle look like to this particular moving observer, right? So what we usually do when we encounter this type of situation is that we define another coordinate inertial frame. So okay, I'll just draw it here. And then this initial frame is moving at a velocity v compared to this original inertial frame. So x, y, z, and then we call it s prime, and then we have x prime, y prime, and z prime. So the same point, this particular point here, when look from this, when we define it with the coordinates in this initial frame, we would write it as x prime, y prime, z prime. And then usually in Newtonian mechanics, we consider the time to be the same, right? So that's that. And we can write the relationship between these two coordinates because we basically know everything, right? You know that, okay, when this frame moves, so you know that this is x, and then this is, wait. Yeah, this is x, and then this is x prime. And this thing moves, right? So technically, you can get the relationship, which is x prime equals x minus vt. And then you have, because it moves in the x direction only, so we have y prime equals y and z prime equals z. So this is called Galileo transformations, and it should be quite intuitive, I think. Are there any questions? We're still in like normal mechanics. I haven't touched special relativity yet. Okay, I'm guessing this is quite intuitive. So I'm gonna move on. You can just put questions in the chat if you want to. So let's move on to like special relativity part. We call them like Lorentz transformation. Okay, special relativity is built on how it's different from this usual classical non-relativistic classical mechanics is that we define two postulates. So the first postulate is all inertial frames are equivalent. And what this implies is that there is no absolute frame, as in there is no absolute frame that is stationary and every frame is equivalent. So you don't have a better frame. Like these two frames are, so basically, like if you look back here, these two frames are the same, essentially. And then laws of physics, sorry. If the laws of physics, if the laws of physics hold in one frame, then the laws hold in every frame, every other frame. So this also makes sense, right? If you have let's say if you have a particle here, if it exists in S frame, it must exist in S prime frame, or else, or else, yeah, or else it will be chaotic. And then the second postulate is the speed of light, c, is constant in every frame. Sorry, in every inertial frame. Okay, if you look back at the postulates, right, we have first and second postulate. The first one is also a postulate. Like you can kind of see that it's also inside the non-relativistic Galileo transformation, right? Like, if the laws of physics hold in the frames in one frame here, then it holds in this frame here. So what's special about the postulate is the second one, essentially, speed of light c is constant in every inertial frame, which is not the case that like how we define here. This is what makes the whole thing complicated. And there's a how people arrive to this weird kind of like a non-intuitive conclusion is that they've done some thought experiments about the Earth, the Sun, and then the ether. You can look it up online. I think it's called something. Okay, let me check. I don't want to pronounce their names wrongly. I think it's something like Michelson. More. Okay, so it's the Michelson Morley experiment. I won't be talking about it here because I mean I think it would be like a 20 minutes detour and then we don't really have that much time, so I'll skip it. And because of this particular second postulate, we get really, really weird, I guess, non-intuitive transformations, as we'll see. Right, so now I'll try to derive the Lorentz transformation to you. Okay, basically this is what we call the Galileo transformations. And then we're deriving another set of relationship between x prime, y prime, z prime, and z, y, x. And then we'll use the relationship to derive more interesting effects in the future, I guess. Also, I'd like to say that Lorentz transformation, there are multiple ways to derive it. Like if you follow Maureen's textbook, Maureen would he will introduce like the time dilation, then contraction, loss of simultaneity, those types, and then they'll use those types of effect to derive Lorentz transformation. But for me, I would like to use just these postulates to reach to the same set of equations. And then after that, after we get those set of equations, we would use them to derive the cool time dilation and length contraction and stuff. All right, let's get started. So similarly, I'll define like two inertial frames. You have S, and then S prime is, as always, moving with a constant velocity v. All right, so first of all, we would assume that the transformation will be linear, or else, let's say we have a straight line, right? If the transformation isn't linear, then maybe, let's say I have a pencil here, and then from S frame point of view, it's straight. But if the transformation isn't linear, then for S prime frame, so it'll be looking, the pencil will be looking curved to him, which doesn't really make sense. So we will assume that the transformation is linear. So technically, we can write something like this. Right, and then you don't copy this first because I'll change it later. So X, Y, Z. And then we have more stuff to do. Wait, there should be another constant here, something like that. Okay, so you get the gist of it, right? Because we assume it's linear, then T prime would be linear to T prime will have a linear relationship to T, X, Y, Z, and maybe a constant at the back. So what we're trying to do, so if we write down the full transformation set, we would technically have 20 parameters to solve, which let's not do that because it's not fun, I guess. Okay, what we do to simplify our calculation, first of all, is we want, okay, we can remove technically the constants here by assuming that the origin starts at the same place. So what this means is, let me just change this. So we just assume like at the start, when t equals 0 and t prime equals 0, like the origin coincides. So, and then it moves to the right like this. So by putting that, by letting the origin coincide with each other, we can remove this parameter. So we're left with 16 because there are originally 5 here, and then you have 4 sets of equation. So if we remove this, then we get 4, and then we get 16 parameters. Now also, okay, let's simplify it further. We will assume because the velocity of the second frame, right, is towards the right, which is like it aligns with the axis of x and x prime. And then we assume sorry, there should be a prime here. So y prime and y aligns also, and then z and z prime aligns as well. So with this, we can technically just simplify it to an equation like this. C t plus dx dy f z. So this is our set of equation, and we just need to solve by using these two postulates to solve it, and then we get a relationship that is kind of, I guess, similar to that. Okay, let's start. First of all, let's consider like symmetrical arguments. So like, let's say I have a particle here, and then if we flip the y axis from this to here, right? So then technically what happens, because this S prime frame only moves to the right, so the y-axis doesn't change. So you know that your y prime would turn to negative y prime as well. And this relationship would hold if e equals 1. And then so we get y prime equals y. Similarly for z, if z goes to negative z, then z prime will go to negative z prime as well. So f would be 1. And then so that z prime equals z. So okay, so we have 4 equations, right? We have simplified this to y prime equals negative y. Yes, okay, sorry. I think I should get it. Okay, if technically the solution for this is e squared equals 1. Okay, basically it doesn't send me a private message just now, and yeah. So technically e squared equals to 1 would also hold, and then we get like equals plus minus 1. But then the e equals -1 solution kind of we will get y equals -y prime, which technically doesn't really make sense, if you get what I mean. So we're like removing this solution. So we're left with just this. Uh, so is there other questions? Why is e squared equals 1? So how should I describe this? If y, if I switch y to -y, uh, okay, let's work with this. Mm, okay, I'll look through it like after the lecture because I don't want to. Yeah, I get what you mean. I'll look at it after the lecture because I don't want to spend too much time thinking about it. That's something that I don't have an answer right now. Okay, so I'll look back to it at it after for my arguments with this part. But okay, we can continue. So we've simplified this to this. Are there any other questions? I don't think so. You can just put it in the chat if there is. And right, okay, so let's consider the case of, okay, we can look back at the coordinates, right? So let's say, okay, just draw it down here. Okay, let's say we look at the frame of, let's say we have a particle that's moving. Wait, does this make sense? Okay, let's say we're looking at the condition when x prime equals 0. What this means is that for this coordinate here, it will move along, it will move the same as this initial s prime frame, right? Then what happens is to uh to this s frame, we would get x equals vt. Then we can use this to simplify our equations here. So for this case, we can plug it into, I guess, 0. Let's plug this into this. So x prime equals ct plus dx. So we will get c equals minus dv. And then we can kind of rewrite the equation as negative vt x minus vt. And then, okay, we're doing another simplification, which is, let's look at so we've considered like this frame, we consider x prime was 0, right? To simplify our calculation. And then like I've told you just now from the postulate that like all inertial frames are equivalent. So like by this way of thinking, let's maybe you can do something with like x equals 0. Maybe you get something. And if you think about it, what x equals 0 means is that this thing like maintains stationary, but if we look at it from S prime frame, then we get X prime equals negative VT, because this stays X is 0 here. Basically, this is X prime. So X prime is basically negative VT. And so let's use this to simplify our equation further. We can plug this into, I believe, this. No, not this. We're plugging it into I. Okay, I'm gonna try this because like I see T and X prime here. If VT equals D, yeah, and X equals wait. Ah, okay, mistake. It should be T prime here. Yeah, so from S prime point of view, this will be like something like this, right? Oh, okay, I'll rephrase it better. So if we look at as if so from S prime's point of view, like the time that has elapsed on like S prime point of view is T prime. So we have this. So like the equation I wrote just now was wrong. That's why I couldn't continue. But anyways, if we plug this inside, it should be, let's simplify an equation that has an X prime and T prime. Okay, we don't have that equation, but we can try to come up with that. So we have to find a relation with X prime and T prime so that we can like plug that in. How we do that, I guess, is we're mainly working with these two equations. So I'm just gonna copy this now. Plus bx x prime equals dx minus vt. Okay, x equals 0. And then for this condition, so it becomes negative vt prime. And what does this do? I want to simplify our equation of AB. Okay, so I'll plug this to inside. We have t prime equals dt. No, it doesn't make sense. Wait. Okay, because x equals 0. So, okay, and then we get these two equations. So basically we have a equals d. And then we can simplify it to be so we can get t prime equals dt plus bx. And then we simplify our equations to these two. And then okay, the final step, okay, I'll just write it here, is we use the postulate, the second postulate here. So let's say I have a, okay, and just in the same diagram again. And let's say I have a light ray that's moving, right? Then we can get, so the path that the photon or light ray traces out is this. But then because the speed of light is the same in every frame, we can write this as well. So this is our final equation. And then if you do the math yourself, the algebra, you can use this, and this. So if you solve it, you get the Lorentz transformation, which is ct prime equals gamma ct minus. Okay, I'll give you gamma and beta later. So these are the Lorentz transformation. And then if you need the full derivation, you can send me an email or something afterwards. But I'm pretty sure it's just algebra because I've just done it just now. And also we have something called the inverse Lorentz transformation. Oh, and also gamma is defined to be this v squared divided by c squared, and then beta is defined to be this. So technically, like after doing all of this, right? I think everyone should do this in their lifetime for at least once, I guess. After doing this derivation, you get this. And then if you do the derivation, if you try to play with the maths itself, you can get this inverse Lorentz transform. So the sign is different. So depending on which frame you're going through and from, it will be different. So be careful with this. Yeah, so that's all for the derivation of Lorentz transformation. And also, like, I want to just say a bit about, okay, let's check, right? Because we have this really cool unintuitive thing, and this happens because we put like the second postulate of Lorentz transformation in. Does this set of equation make sense when it's like velocity is smaller than so much smaller than c? Then basically the question is, does this go back to this? So it's kind of like a sanity check, I guess. And it's always good to do that when you're solving problems. So you can quickly check that it basically gives the same. So can simply go through it. If b is smaller than c, right, then very smaller than c, then gamma would be approximately 1. And then beta would be approximately 0. And then you can technically kind of check that it goes back to this original Galilean transformations here. So that's it for Lorentz transformation. Okay, we can move on to the cool effects if nobody have questions. Okay, so I'll need this. All right, so if you've heard of relativity before, then you've probably heard of those type of time dilation, length contraction and stuff. So we'll be using this Lorentz transformation that we have derived to, I guess, get this type of cool time dilation and length contraction effect. Okay, so let's get started. I'm just gonna make a table here. Okay, let's talk about time dilation, I guess. So, if you follow Maureen, right, I guess you can. There's like a really cool time dilation derivation. Like if you have I think a train, and then you have a light source, you have a mirror here, and then the light goes like this, and then so if a person is standing inside and a person is standing outside, and the train, let's say, moves it like a velocity v. Uh, you can find the derivation online, but basically you can derive the time dilation this cool way, and like you use tricks like the speed, and because the speed of light is constant, the distance here and the distance here is not the same, and then because c is distance over time, right, for the light traveling, then you get, because distance is not same, but then c is same, and then you get a different time. That's one way to derive it, but I'm just gonna check this by using our Lorentz transformation here. And how we do that is basically just think of it this way. So I have two frames and same thing. I'll be drawing this diagram a lot of time, but all right, it's fine. Y prime, X prime. So time dilation basically is a special condition of Lorentz transformation when X prime equals 0. So, oh yeah. Pythagorean theorem. Yeah, I agree. Because, okay, let's say I have a particle, let's say I have a particle moving, and then like we have an observer, stationary observer here in S, and then let's say we look, let's say we have another frame, S prime frame here. Can I define it? Okay, I'll do that later. Let's say I have another frame, S prime frame, that is moving the same as this with the same velocity as the particle moving. Then we can say that S prime frame is kind of like with the same frame as the particle, right? Okay, and then does that ask me to define proper time? Okay, let's define proper time. So proper time tau is basically, do you have? I think it is the time of the. I don't remember the exact. Can you, Zizan, can you give me the exact definition? Okay, I
Yeah,
remember what it is, but yeah.
proper time is the time interval experience in the frame itself. So if you're co-moving with the observer, that's the time interval that you experience.
So basically, what it means is that when this S prime frame, which is co-moving to this particle here, then the observer that's co-moving through it sees the time with the particle moving. That's called a proper time, I guess. I don't have the exact definition with me,
Yeah, there's so
but
there's
yeah.
two different times here. That's why they're both like dilated. Like one's dilated relative to the other. So there's a coordinate time that's in your own coordinate frame, and there's a proper time, which is what you think other people feel. So there's a t and tau. Yeah. Oh, t prime should be tau, but yeah, coordinate time should
Well,
be
I
just yeah.
mean, tau equals t prime when the conditions are met, which is x prime equals 0. But yeah, okay,
Wait,
this is fine.
that is by definition, right? Because you're co-moving with the
Yeah,
observer, therefore x
yeah,
prime
yeah,
equals
yeah, yeah.
0. Yeah.
Yeah, but I don't want to confuse them with tau and t prime. Okay, so basically because these two frames are the same, like this S prime frame is co-moving with this particle, x prime equals 0, and then we define, uh, if you look back at this, okay, so there are two different, okay, as Susan said, there are two different times here. The first time is like from a stationary point of view, and then the other time uh, from this co-moving frame itself. Because from these transformations here, right, you can see like the time is not the same as this time anymore. Like there are two different times depend on which coordinate that you see it from. And then let's say S prime is moving co-moving to this particle, then X prime equals 0. And if we plug this inside Lorentz transformation, I should be using the wait, I should be using the inverse transformation. Let me check. Yeah, I should be using this inverse Lorentz transformation instead. Okay. So, I mean, these two sets of equations, like I've told you, we can use interchangeably depending on which frame you're boosting from, to and from. But there are equations that we can use. Then, okay, if we check back at the equations here, x prime equals 0, and if we plug this in this one, and And then x prime equals 0. So we have this. And then t equals gamma t prime. So that's time dilation. Basically, what it means is that for an observer in S, it would it will see a lot because gamma. Okay, gamma is this, right? 1 minus v squared divided by c squared. And you can check that it's actually larger than 1 because v can't be larger than c. Then so this thing would kind of be like a fraction. And if you divide 1 by a fraction, you get a number which is larger than 1. So you can see t is larger than t prime. And this is what we call time dilation. Basically, the observer here and the observer in S prime and the observer in S would experience a different time. And for this case where x prime equals 0, we define t prime to be tau, which is the proper time. This is kind of like the definition of proper time. Yeah, I think this is kind of confusing, but you can take it as it is, I guess. If you have questions, just put in the chat. Okay, then let's move on to length contraction. Same thing, you probably can derive it the other way, like if you follow Morin or some other textbooks. But I'm just going to check that it's length contracting here. So let's say I have two frames, the same diagram again. Okay, I'm gonna stop drawing the z-axis because it takes up some, it gets kind of cluttered up. But anyways, let's say I have something that has a length, let's say I guess a ruler with length, I guess I can write proper length L naught. Okay, so we define proper time just now, right? Then we can define a proper length, which is the length of the ruler viewed by the observer in the S prime frame, which is co-moving through the ruler itself. So this would be, in our case here, L naught would be X prime. Okay, also length contraction basically, okay, how do you define like a length of something? Let's say I have my pen here and then you have a length, which it means that you take the distance, sorry, you take the difference between the distance of this point end point here and this point initial point here, right? So we basically just take the initial point as x prime equals 0, and then let's say this is x prime equals L naught. And how we define, basically what we do is like we measure the difference in length. So we measure, and if we set this as 0, like the distance of this should be 0, then we're actually just measuring the distance here. And we measure that with a time, right? We need the time when we measure both sides is the same. So technically, the observer in S, let's say I want to measure, so the observer in S prime will see the length as this L naught, which is the proper length of the ruler. But let's say for observer in S, then we will see, what he will see is, he will measure it at a time. So let's say t equals 0. Then if we put this back into the equation, x prime equals, okay, we can put this inside this equation. So x prime is, and then t equals 0. So, and then if you arrange it a bit, it will look like this. So this is the length that I see from my stationary frame, right? And then this is the length that I see if an observer co-move with the ruler. And then gamma is larger than 1. So the length that I see as if it has been shortened. So that's length contraction. Is there any question? I mean, if it's your first time hearing this, then it should be quite confusing because it still confused the hell out of me now. So, yeah. Okay, if no questions, I'll move on. And also, one of the consequences after time dilation and length contract, you probably heard of this too. But another thing that I want you to know that you have a loss of simultaneity. So what this means is that because you have two times now, and like the two times are different. So what it means is like if something I think a good way to phrase this is like two if an event happens in one of the reference frame, then it might not happen the same time in another frame. I mean, okay, I don't want to get into math of that because like we don't have much time to finish the other stuff, but just keep this idea in mind. You can check up derivations online when you actually need them, I think. All right, so we're done with the cool effects part, and then we can move on to velocity addition, I guess. Okay, same thing. I have two frames, S or S prime. Let's say I have an object moving in the S prime frame, which has the velocity, I guess. Okay, this is V. So we need to define another alphabet for the velocity here. Let's call this U prime. So this object is moving in a speed of U prime from the frame of S prime. And then our question is, because you have time dilation and length contraction, or technically we have Lorentz transformation here, right? So if the velocity of the ball is viewed from S frame, it wouldn't be the simple U prime plus V. Because I mean, this is the Galilean's transformation case, but it's not the case for Lorentz transformation. And I'll be deriving this with you. So okay, let's define the velocity. So we have U prime equals delta X prime divided by delta T prime. And then U, okay, what is U? And then you have the velocity that's viewed from the S frame itself. And then I'm going to try to use these two definitions with combining with Lorentz transformation to get the velocity addition formula. So we can try. U prime equals, okay, I'm just going to plug in the Lorentz transformation equations. Wait, yes. Okay, okay, I'm confused. Basically, we define, because we put a delta here, which is how it should be the case. But if you look back at this Lorentz transformation, right, it's only, you don't have the delta because you don't have the change here, right? Uh, I guess a nice way to phrase it is, instead of writing this, the more correct way to write it is C delta T prime equals gamma C delta T minus beta delta X. But then because they add up kind of like the time, you can add up time, right? And then you can add up distance as well. So we kind of just take out the delta here and you get this. So technically we can just plug in, same thing, we can just plug in because I want to use this delta version of the Lorentz transformation and to plug them in, but yeah, just to talk about it. And then you have this. And then this is gamma C delta T minus B delta X divided by C. Yeah, the units make sense. Okay, okay, I'll just sorry, it's a bit confusing. Let's do it properly. So I have these two equations, and then we just plug in this in here, right? We just cause we put a delta x here, delta x prime, delta x, delta t, and then you have c delta t prime, c delta t, and then delta x. And then for this delta t prime, because the transformation is here, there's a c factor I have to transfer to here, and that's why I have a divide by c here. Also, another thing to note about, like, I guess Lorentz transformation is that you can write it in like a few ways. One of the ways that I like to is to write like this, but then some people write without the c as well. So you have an extra t minus beta divided by cx here. But it depends on how you like to write it. I like it this way because it makes the units the same. Like, because time has a different units as distance, and writing it with a c in front makes them having the same unit. So this is, I guess, nice. Okay, we can continue. So the gamma can be taken out, and then you have a c. Let's move this up here. Okay, then again, going back to our aim, we want to find the relationship between these two. So let's try to get delta x divided by delta t out. So you have, let's divide both sides with by delta t. And then more math to do. Okay, let's just plug u in first. U minus beta c. Okay, let's write beta, because beta is v divided by c, right? Let's write it like this. And then you have c minus v divided by cu. And when we divide up and down by c, you have this vu divided by c squared. So that's velocity addition. Let's look back at the equation, the formalism again. So what we're doing is, like, we're trying to find what the velocity of this particle looks like when seen by S frame, when the velocity is u prime when it's seen from S prime frame. So we get this equation. Okay, now we can check if this is the relativistic version. We want to check if it kind of obeys, I guess, the non-relativistic version. So what happens is you can basically take okay, I think one of this, we're doing some sanity checks, right? And then I think a nice way to see things is, I guess when v equals 0, then you get u prime basically equals, yeah, u. That makes sense. Because, like, if S prime is not moving, then obviously they will see the same velocity. And let's say u prime, okay, u prime is true. I guess this is fine. You can do some other sanity checks yourself after, I guess. Okay, that's all for velocity addition. Okay, just to recap a bit. So what we've done is, I've introduced to you Galileo transformations, and then I think Galilean or Galileo. I think Galilean transformations, right? Galilean. Yeah, my bad. The Galilean transformations. I've introduced you to the non-relativistic version of this, and then we work our way step by step by deriving. I kind of skip some stuff, like some algebra here that you can do it yourself after lecture. And then we get the Lorentz transformations, and then you get the inverse one. But you can get them by playing around with maths. And then after getting the Lorentz transformation, we use the Lorentz transformation to do cool effects like time dilation, length contraction, and then now that I've talked to you about velocity addition. So are there any questions so far? If not, then I'll continue. Okay, we can continue and talk about space-time, I guess. So, what we're seeing here is like you have these types of like Lorentz transformation, and because time in one frame is different from time in another frame now, and what you usually see in 3D is for non-relativistic classical mechanics, right? Time is a quantity that is uniform throughout, and then coordinates is only defined by three variables like x, y, and z. But then for special relativity, because of Lorentz transformation, time cannot be separated from the three dimensions of space. So what this means, right, is let's say, okay, so in 3D we have, by Pythagorean theorem, you have a distance which follows something like this. But then because Lorentz transformation would need another, I guess, a distance. So what we do is we define something called this, which is, let me write this now first. Delta t squared minus delta x squared minus delta y squared minus delta z squared. And like everything that we've done in non-relativistic classical mechanics is like everything is done in 3D Euclidean space. But now that we have included, now that we've said time cannot be separated from three dimensions, we kind of like have like a 4D. And then we're working with, wait, sorry, this is 3D Cartesian space. And then we're working with 4D Euclidean space. So, so we would now start to write our coordinates as, because usually you write the coordinates as x, y, z, right? We want to write our coordinates as ct, x, y, and z, which is called the space-time interval. And then you have this equation here. We call delta as the invariant interval. So okay, should I talk about that? No, okay. If you've probably seen it written as like if you're doing general relativity in the future, this is also called a line element. But yeah, that's just to let you know. Okay, so let's look at this thing here. Let me just write this down. Okay, so for 3D, right? Let's say I have a point, like I have distance. So I have two frames, right, in just non-relativistic classical mechanics. Then you know that delta L squared would be the same for the two, I guess, distance that you see from two different frame of reference, two different inertial frame of reference. Like these two would be the same. But then for 4D, because of Lorentz transformation, this thing holds as well. Y prime squared. So this thing holds, and you can actually derive yourself. You can just plug in the Lorentz transformation here, and then you see that these two are equal. So that's kind of like a difference from the non-relativistic classical mechanics, I guess. And okay, we call this the so because it remains the same in different inertial frames. And then we have already because we already have too much stuff that changed. Time change, like x change, y change, z change. And afterwards we'll see like momentum change when you switch frame of reference, energy change frame of reference afterwards. So it'll be nice to have something that doesn't change when you switch frame. And coincidentally, this thing is something that doesn't change. So it's nice to have it there. And I guess we can take a look at this equation here. So, okay, I'll remove the deltas. And let's say we are only looking at like x direction. So s squared equals c squared t squared minus x squared. Again, we can technically separate this to three cases. Okay, let me write it. First case is s squared equals 0, s squared larger than 0. What it means is that c squared t squared is larger than x squared. So you know that we call this the okay, we will call this the time-like separation. Because the like if you look at it, the time it how should I okay, maybe I should write it this way. T is larger than so for a s squared larger than 0, you can look at it and then say that or maybe okay, maybe a way to write it better is like this CT. Then what it means is that your x is smaller than CT. So it can information within this S which is larger than 0, information can travel because you know things cannot travel larger than the speed of light, right? And then x is smaller than CT. So what it means is like information can travel within this S itself, and we call this time-like separation. So we can look at the two other cases. So when s squared equals to when s squared is smaller than 0, you have space-like separation because c squared t squared will be smaller than x squared, and then your x would be larger than CT. We call it space-like separation. And also you have another first case, second case, third case, and then you have s squared equals 0. We call it the light-like separation because CT c squared t squared equals x squared, and this holds. Also, another thing to note is that depending on which textbook or literature that you use, we have two different versions of delta S. The one that I use here is this, but then some people define it this way. But I mean, it's just convention, or it's just a matter of convention, and just choose one and stick to it, and you'll be fine. The one that I like to use is this one. I think more of the general relativity people use this, but I'm not sure. But yeah, just to keep in mind and don't confuse yourself when you see another type of convention. Yeah, I mean the GR people use the second way, but I mean I like the left the first one more so. Plus, I mean it's just a personal preference because I used it when I was studying like special relativity in high school for Olympiad as well, so I still stick with it. Also, I haven't taken the actual GR course, so I don't know. If you've done that, then maybe it's superior. I don't know. Anyways, okay. Let's look at it's two now. Should I talk about? Okay, I'll talk. If I have time, I'll come back to space-time Minkowski diagram. So I'll move on to dynamics. So are there any questions before I move on to the next section? I don't think so. I guess we can move on. All right, so what dynamics is in non-relativistic classical mechanics? You have F equals ma, you have F equals dp dt, and then you do your stuff, you do your integration, you get P equals mv, and like you also get kinetic, you get the work energy theorem, kinetic energy equals half mv squared, something like that. Wait, sorry, I think I have to charge my laptop. Wait, give me a second. I need to charge my laptop. Okay, nice. So, okay, like dynamics, you have this type of stuff, and then because we have Lorentz transformation now, technically what we do is we redefine, okay, I guess a nicer way to phrase this is because your velocity is already weird now. You have the velocity addition formula here, and so what we like to do is we like to redefine momentum and energy, and we define it to be gamma mv, and then the energy to be gamma mc squared. Basically, you can look at it this way. So if what we want for momentum and energy is like we want them to be conserved in a reaction or collision or whatever, so that it conserve and we can use it to solve equations and get the velocity that we want. Then in our case, because we need to redefine momentum and energy so that they conserve and we can use them to solve equations. And okay, I'm not gonna do a proper. I'm not gonna show you here, but if you can try to show it yourself afterward. Like you can do some. You can try to find like collisions to do, and then you realize that this doesn't really hold anymore, and then we need to redefine them to this. And like it kind of recovers back as well. Like for the momentum at least, like when it's non-relativistic, gamma is approximately 1, and then you can recover P equals mv. And okay, the energy is more interesting, I guess. So okay, the energy is more interesting, and I'm going to show it to you. So we'll write the gamma as its full form, something like this, and then you have mc squared. And now, when it's the non-relativistic case, right, this thing is so much smaller than 1, and because I can write it, I think this would make it more appealing. We can technically do a binomial expansion. Like you have something like this, right? Approximately equals when x is small. Dot, dot, dot. So if let's say we do a binomial expansion plus nx nx, so it will be half b squared divided by c squared. Let me just move it to the other side. Okay, we can plug in the MC squared inside here. I'll write it this way. So we get MC squared plus half MV squared plus 3 divided by 8 V4 of force divided by C squared. And then you have some other terms at the back. So if you look back at this equation, okay, I'll just write it like this. So we've redefined energy such that when we expand it in the non-relativistic case, we recover the, I guess, rest mass energy, you can call them. And then this is basically the kinetic energy term. And then you have a bunch of some really random terms at the back. So what it tells you is this, like in relativity, the full form of the energy, when we approximate it, so there are like a lot of random terms at the back that we don't see in non-relativistic classical mechanics. And because the velocity is small, we only see this kinetic energy term. So I think that's quite cool, I guess. And we call this the rest mass energy. Okay, I think if it's your first time hearing rest mass energy and stuff, right? I think a point is to not confuse yourself, because I think a lot of people, I think some of the older relativity textbooks define mass as something like this, and then you have rest mass or something, and then this is like the mass when it's moving in some frame. But I don't like to look at it this way. I mean, it's not wrong, but the newer versions usually just write it like this, so you can just ignore the whole rest mass argument here. Then now that we have redefined energy and momentum, let's look at the relationship between these two terms. So in classical mechanics, you have E equals p squared divided by 2m. But now in relativity, they have a different relation, and let's calculate this ourselves. We can try to do E squared equals, okay, I'll do it the other way. So E PC squared plus, okay, let's try to calculate this term, not this term, this equation. So we can put in, okay, R, okay, this is confusing. Okay, I'll remove this because I think that's confusing. Or wait, let me. Oh, it's not even classically. It's non-relativistic. And then this is relativistic. Okay, same thing here. We have non-relativistic. This is relativistic. Gamma mv equals gamma mc squared. Okay, let's try to calculate this particular term. We can plug this in. Squared c squared divided by gamma. So gamma is 1 minus b squared divided by c squared. So if you square it, you just take out this square root here. 1 minus b squared divided by c squared plus m squared c to the power of 4. Plus m squared c to the power of 4 minus m squared v squared. C squared. Yeah, I guess yeah, okay, I don't think I've done any mistakes. And then we get m squared c to the power of 4 1 minus. And then let's write this as gamma squared m squared c to the power 4. So this is just gamma mc squared, which is just the energy squared. So we've written down a relationship between momentum and energy, and it takes up this form. So for non-relativistic and relativistic has two different relations. And I guess this is kind of useful, as in, how should I describe? I'll talk to you how it's useful later when we define the four momentum. But yeah, just keep this equation in mind. And okay, I guess a thing to note is that when we're doing problems, right, we conserve energy, we conserve momentum, and then we use that to find a velocity. So the takeaway is that try to for like collisions and reactions, try to use conservation of momentum and energy to solve that for the momentum and energy, and then use it to find the velocity instead of finding a velocity directly. So that will make your life easier. And also, I guess you can use the relationship, which is because like just from these two equations, you can technically see that this is just v equals. Okay, I'll just do it properly. Gamma mv, you have E equals gamma mc squared. And then you divide these two equations. And so this is just B and then C squared. And then just by finding momentum and energy, you can get the velocity directly. So yeah, that's that. Do I have? Also, I guess one thing to note is that if you use some textbook and then you might see them setting C equals to 1, just to make the algebra easier. That's something that I guess physicists do because you can easily recover the units themselves. Like let's say for this particular equation, right, I can just write directly p squared plus m squared equals e squared. And then, well, I mean, it's wrong, like if you talk about units, but then I can easily determine what units it is and then just plug it in. So like that's just a side note, I guess, in case you see it in the future. Okay, we can talk about for momentum now. Are there any questions? If not, I'll move on. I'm gonna assume there's no questions since everyone's silent. Anyways. Okay, like I've talked to you up here that we've defined this like space-time interval, right? So we're using, if we treat this as a vector, then it's a vector with four components. It's a vector with four components, 1, 2, 3, 4. So similarly, we can define them, and then you have time here. And then similarly, we can define kind of like a vector with four components with energy and momentum. And then you realize that they kind of they have their own Lorentz transformation. And basically what we do is like we define lots of these things called four vectors. And then they obey their own Lorentz transformation. And one of them is the four momentum. So I usually like write it like this: E divided by C, Px, Py, Pz. Okay, I'll just put this here just for you to compare. And Like just now, like while I was talking about the space-time interval thingy, you have this thing. So similarly, for this for momentum, we can define kind of like its own norm. We call it norm. Basically, for the usual vectors, we call it the three vectors. We call it the three vectors. Like let's say you have, I guess L equals X, Y, and Z. And then the modulus squared is basically X squared plus Y squared plus D squared. And then just now I've defined to you that, okay, maybe I'll write it like this. X squared minus Y squared minus Z squared. So similarly for this four momentum, right? We define a norm squared for it, which is E squared divided by C squared minus P squared, Px squared, Py squared, Pz squared, which is E squared minus C squared minus, this is just P squared. Or I think a better way is to write it like this. Then please don't confuse yourself with like the three momentum and four momentum. There are two P's here. And also, okay, I said this equation was useful just now, right? It's useful when, like, can you see kind of like the relationship between them? Basically, what it is we can rewrite the equation. Wait, this shouldn't be here. We can rewrite this equation to be squared minus PC squared equals MC squared squared. And then you divide both sides by C squared. So technically this is just M squared C squared. And yeah, so four momentum is useful because like the norm squared of it is just the, I guess, rest mass times some speed of light to make the units correct, but that's the gist of it. And similarly, because we said that S squared is invariant when I transform frames, right? But going back to here, you can prove it. I told you can prove it yourself that it's the same in different initial frame. Similarly, the norm squared of the four momentum is just the rest mass of the particle or object. So it doesn't really change when you switch frames. Momentum and energy itself changes frame, but for momentum squared doesn't change frame. Sorry, change doesn't change when we switch the frames. Yeah, and then you can use this for momentum thing to solve problems. As in you usually solve problem by equating E equals like initial energy equals final energy, and then momentum initial equals momentum, and then I mean it's a vector, so we have three more equations. But then you can actually just use the four momentum to solve problems, which usually gives a quicker way to solve problems because of their own property like this, which is this one. I mean, you see when you start to solve problems. Then I'll move on to acceleration. Actually, okay, so I've postponed acceleration until now because I think it's better for it. It's better if I structure the course this way. Like if you look back at non-relativistic cases, F equals ma equals dp dt. But then now that we've redefined momentum and then acceleration, we still haven't given it like a proper like definition. So we're gonna do that now. We want F to be dp dt, and then we want the acceleration to be du dt. This is how we want to define them. Or you could do it the other way, which is like if you follow Maureen's, I think oh no, sorry. They introduced four. I told you there's like four vectors here, and then there's actually something called like the four acceleration that you can read up after, but I'm not gonna talk about it. Like they also define acceleration. They also define acceleration their own way, but I'm just gonna talk about the three acceleration here. Then okay, let's look back at this diagram. Let's say I have an object which is experiencing a force. Uh, so the force will look like F prime in S prime frame, and then you look as like the force will be F when measured in S frame. Then we know that F prime basically equals. Wait, should I write it like this? Yeah, this makes sense, right? Because in this frame, in this initial S prime frame, this should hold because there's no like Lorentz transformation and stuff. But then what now we want to know what does the particle feel with the acceleration and forces when we're seeing it from this S frame. So we're gonna do some differentiation. Basically, we've redefined P to be gamma and V. Then F is basically just dp dt. So it's just d dt gamma and V. Okay, so it's just some math. We can do this. D gamma dt mv plus gamma m dv dt. We're taking like mass to be constant, so I'm not putting it inside the product rule. This is just the acceleration, and we want to find this. It would just be this 1 minus b squared divided by c squared. And then it is 2v divided by c squared and then dv dt. Sorry, wait. There should be this thing here. So this becomes A. And then you have gamma cube. Where is this? Should be. Does the units make sense though? Wait. I guess they're okay. Gamma cube beta A divided by C. Okay. Now I plug this in, and then I get gamma cube beta A and there's a C here. MV plus gamma MA. And then I don't have space. Okay. And then V divided by C is just beta. We get this. To simplify, we want to simplify further. I'm just gonna take the gamma MA out, plus 1. Okay, so we can technically evaluate this. Should I do this? You can try to prove it yourself. Gamma beta squared plus 1 is basically just gamma squared. It should be, yeah, it should be gamma squared. And then you get gamma cube MA. This is just expansion, like it's just 1 minus beta squared, and then you have beta squared plus 1. You can do the math yourself. It should be just gamma squared. And then you get this. So what it means is that for a object moving, and then which is experiencing a force. So if we look at it as an stationary observer, we will see this equation. So F does not equals MA anymore, which is why I wanted to like delay it until now, because it's kind of counterintuitive, but with it makes sense, I guess, if you've done the derivations properly. So that's the 1D case, and this case holds when like the force is the same direction as where the velocity of the frame is co-moving to. Technically, you can also do a case where when the force isn't the same direction, let's say like I want to define a force here, and then you can separate it to two directions, one parallel to this velocity here and the other one perpendicular to it. So same thing, we define this thing, and your P would be Vx, Vy, and this would be 1 minus V squared x divided by C squared. Should I, is this too quick? Okay, I'll do it properly. So Px is gamma mVx, and then Py is gamma mVy. And then your gamma is square root, or 1 divided by square root 1 minus V squared divided by C squared. And then your V can be separated into X and Y component, right? So if you do it properly, you get something like this. That's why you have like the X, Y's here, and like this is like a 2-component vector. And then, yeah, just differentiate it. And we take a condition where Vy is 0 initially. Okay, I'll write it like this. We're assuming like the velocity of y is 0 initially. And if you differentiate this yourself, you basically get F equals gamma cube AX gamma AY. So what this means, right, is Fx equals gamma cube MAX, Fy equals gamma MAY. Like the forces, depending on the direction that you're acting on it, gives different, I guess, you can view it as like they have different contributions of gamma. And why this happens, right, is because you have it's related to time dilation and length contraction. So because like how should I describe this? They have you have Fx here, right? And then because you define it to be d squared dp dt. Wait, sorry, let me think of my argument. I think I confused myself. Okay, I see. Okay, never mind. I think my argument only works when. Okay, you can ignore what I said just now. Basically my argument was more towards like Lorentz transformation when when you transform between two accelerations, but we're not calculating that, we're just calculating the force. So if you just follow the math, then you have these two equations. And then just to say again that f prime x should be max prime, and then f prime y equals may prime. So you have the acceleration in the stationary frame. Do you have any questions for now? No? Okay, we can, since we still have 30 minutes, I'll go back to the Minkowski diagram. It's the place here. So I'll be continuing from this space-time part. If you're copying, like I'm gonna send this PDF to you all later, so you can copy after or something. Then, so going back to kinematics. Okay, if we look back at this space-time, right? Okay, if we were saying, if you're looking at Cartesian space, then we would just write y, x, and then you have your diagram, Cartesian diagram. But then now that in space-time, time is not separatable from space, what we usually draw is like a Minkowski diagram. So it's like CT here and X here. So maybe I can put a Y here. Well, I mean, I can't draw 4 dimensions, so this is the best I could do. And then looking at back at this delta S thing, so technically we separated this S to 3 different regions, right? I can technically separate them the same way here in this diagram. So I'm gonna draw something like this. It's just a pop. I'm thinking if like there's a better way to phrase this. Well, I guess this is fine. So we can look back here. We draw we call this the light cone, and what it means is if it's in 2D, right? CT and then X. So this is like a 45-degree point, and if I turn this 1D to 2D, then we get a light cone. And technically, for this equation, is CT equals X. So you have the slope equals to 1, which is like tangent theta equals 1, and then theta is 45. What this means is like when a light travels with a speed of light, then it would travel with this path. And anything, so things cannot move faster than the speed of light. So technically, any object that has mass, that any object that has mass cannot travel like in this region here and this region here. That's not possible. The only region that they can travel is here and here. Maybe I should color code it. This is travelable, and then this is non-travelable. So going back to these 3 cases here, we can see that like this region here is basically just time-like separation, so that information can travel within the light cone itself. Like the information can travel within. So any events that are not like that crosses this, like any event that are in this red portion that's not within the light cone cannot technically interact with each other. We call this like the cone of causality. And then the lines are just the light separation. Okay, so that's all I have to say about this, and then I'll move on to the proper formation of Minkowski diagram. Okay, so a way to look at it is let's say, okay, looking back at non-relativistic case, if you have a point, and when you rotate a point, should I? And then let's say I have a frame of reference that's rotating, that's like rotated compared to the original frame, y prime, x prime. Then you get something like this, right? X. Okay, this assumes kind of like matrix knowledge already, but if you've never, how should I describe this? If we're doing rotations and if we're doing rotations, we basically, if you've learned matrices before, we can write this, we can write the equations like this. The theta is the angle between these two frames. Cosine theta x prime y prime. This is if you do a rotation in just 3D Cartesian space. But for relativistic case, right, we're defining the axis to be ct and x. And okay, it is, I guess, okay, one way to look at it is like, what we want to do now is we want to write the ct prime axis and x prime axis on the same diagram, just as we wanted to do here. So what we need to do is, for ct prime, okay, let's say we look at the x-axis. X-axis basically means ct equals 0. We want, it's the line where the time itself is 0. And then same thing, ct is just the line where x is 0, right? Now we want to find the line of ct prime and x prime. And x prime itself means ct prime is 0, and ct prime is 0. Ct prime axis means x prime equals to 0. And we want to put it here on this diagram. So what we need a relationship of these two different inertial system, and we use again Lorentz transformation. Then ct okay, I'm just gonna copy it down. Give me a second. Ct prime mean, okay, let's find this axis here. It means x prime equals to 0. So technically, if you want to find like the Lorentz transformation, we need to find one with x prime so then we can plug this condition in. And we want to find the axis in this ct frame and x frame. So we need an equation with x prime, t, and x. And the perfect equation for that, let's look at it, should be this one. Yeah, this one. So if I plug this in, right, ct prime axis, this equals gamma x minus beta ct. So ct equals 1, sorry, x. So you have the slope. Like this is your y-axis, right? And then this is your x-axis. Y-axis, x-axis. You have the slope of this ct prime axis. And then similarly, if you do it for the x prime axis, t prime equals 0 equals gamma. We're using this equation here because we need the equation that has t, x, and t prime, because this is 0. Then, sorry, ct minus beta x. So ct equals beta x. And you know that your beta, okay, beta is defined to be v divided by c. And so the maximum value that you can get is c, right? Because sorry, you can get is 1 because b cannot be larger than the speed of 1. So this should be in between 1 and 0. So basically what this means is that there will be a slope like this. So for your x prime axis here, and then ct prime axis, which is something like this. And then you have this is okay, let's just say this, sorry, let's just say this is theta. And then you have tangent theta equals beta. I mean, because like the tangent of the slope is the gradient of the slope, right? And then similarly, you have a theta here. And this is what we call a Minkowski diagram. Okay, just to recap, like if I have two reference, two initial frames, and then one is moving v, and then your beta of this frame is v divided by c. We can draw a Minkowski diagram such that this is the original rest inertial frame, and then if you look at it from a moving frame, its axis basically would be slanted this way. So it's not, these two axes are not perpendicular to each other anymore. Also, a thing to say about this is, okay, let's look at point x prime ct prime equals 0, 1, right? So what this means is that x prime equals 0. So it's on this ct prime equals 1. So it's this point here. Let's say we look at this point. And we can look at the Lorentz transformation of this point to, okay, it's the inverse Lorentz transformation, but let's find the let's find the xct. Again, we have to use Lorentz transformation. We're using the inverse Lorentz transformation now. So x is this, x prime plus beta ct prime. X prime is 0. So gamma, your beta c. Yeah, should be correct. Let me check the units. T. Yeah, okay, the units are correct. So we can put this in gamma, beta, c. And then you have ct equals, we're using this equation now. So it's just gamma because this is 0. Okay, what this means, right? If you look at it, the modulus square of the, like if you take the modulus square, ct prime squared minus x prime squared, it's 1. But then the modulus squared isn't the same here. So 1 unit here is not 1 unit here in ct. So it kind of gets stretched out, I guess. And you can look at it like if you do this thing. If I want to take just the modulus squared, you have gamma squared, beta squared plus do I want to take c equals 1? Wait, let me check the units a bit. I'm still confused. Should be correct. Okay, I see. Bruh. Okay, ct prime is 1, so this should be 1. Okay, you have gamma beta. This is just gamma beta. And then if you take the absolute value of this, it's essentially 1 plus beta squared, and then gamma squared is this thing, right? So you have square root 1 plus beta squared divided by, wait, sorry, this thing. Okay, I don't think I can simplify this further. And then you know that beta square is larger than 1, larger than 0. So this term would be larger than 1, right? So an axis, so in the CT prime axis, a unit, like a 1 unit here, if we look at it from a CT unit, like the original frame, it gets stretched out, if you get what I mean. So it's not like 1 unit here is 1 unit here. 1 unit here is basically this much unit here, in the original frame, original rest frame. So that's Minkowski diagram, and technically you can use this diagram to kind of solve for. You can use it to derive your time dilation, length contraction, everything. I believe you can find this from textbooks. So I won't be doing them here, and also we're kind of lacking of time. So I'm going to go into rapidity, and we'll call it a day in like 10 minutes. So okay, now we define something called the rapidity. This is kind of like out of the blue, but technically, if you try to do this whole Lorentz transformation thing yourself, like this derivation that I skip here, then what you realize is the solutions kind of represent, it kind of has the form of hyperbolic function, hyperbolic trigonometric functions. So if we define a hyperbolic trigonometric angle here, let's say we call it, so basically we define this thing called rapidity such that it follows this thing. Sorry, omega, I'm not sure if it's W or omega, but it is what it is. Hyperbolic tangent rapidity equals beta, then it would make our calculation a lot simpler. So why this thing is, okay, let's look at it this way. So you remember you have a velocity addition formula somewhere here. You can also like write out another in velocity addition, like if I switch these frames, right, then I will have this equation myself, plus v divided by 1 plus u prime v divided by c squared. I'm going to put this down here. And if I write it in terms of beta, I'm just going to write it like this, I think. Beta 2, beta 3. Yeah, this works. So if I divide by c, right? Divide by c, and then I get beta 1 equals, this is beta 2, beta 3, 1 plus u prime divided by c is beta 2, and then v divided by c is beta 3. So this thing should look, okay, if you've done hyperbolic trigonometric functions, this thing should look familiar to you, as in it fits this hyperbolic hyperbolic tangent addition. So it would fit this thing. Actually, okay, I'll just use the same subscript so that I don't confuse you. So they technically have the same form. So we can define this thing here, and then it will be quite useful in the future. Like, and then we can use this to find hyperbolic sign. Okay, I can give you the answer, but technically you can derive everything yourself from the identity, hyperbolic trigonometric identities yourself, and then you have cos. This is gamma. What this means, right? If we look back at Lorentz transformation, I'll just copy the thing down again. You see T. Okay, I'm just gonna look at these two. So I'm gonna skip Y and Z. And this is gamma CT minus gamma beta X, and then you have X prime equals gamma X minus gamma beta CT. If I plug this inside here, right, we'll get something like this. Gamma X quotient CT minus, and then you have X prime equals gamma beta CT. Or if you write it the other way around, uh, let- okay, since I've written this like this, I'm gonna write this other way around. I can technically write it as, if I use the inverse Lorentz transformation, CT prime minus BX prime, and then X, sorry, this is plus. If I plug in the gamma and gamma beta to this hyperbolic trigonometric identities, you will realize you can write a matrix like this. So it would be this. So if you compare this matrix here back to this rotation matrix in 3D space at the start, they look similar, right? So what this means is basically Lorentz transformation is technically just rotations, but in 4D space. But because we're not working with Euclid, we're not working with Cartesian space, we're not using like usual trigonometric identities, but instead we're working with 4D Euclidean space, and hyperbolic trigonometric identities suit it more. That's why it's like a rotation, but yeah, it's a rotation in 4D space. I think that's it for the lecture today. That's all that I want to talk about. I feel like I want to look back at this thing that I was stuck here. So I think I'm done for the lecture. I'll send this PDF to you all afterwards. But I want to look at this thing. So that I kind of got stuck at the start. You can leave if you want to, or you can stay if you want to look how I fix this thing. So okay, let me look back at like the message didn't send me.
Hello.
Yeah. Y prime
I think the
your
problem here is that
dimension.
hey,
Sorry?
wait, by the way, do you still want the recording or should I just like stop it? Yeah.
I think we can stop, I guess. We
All
can
right.
stop.
Thank you for watching.